So we take these boxes, we see the number of zeros here, and then we sum over all the moduli up to a certain level, which is t. Okay, and then we get some bound for that. That's where we stopped this morning. I mean, before lunch, we stopped here. So, yes, I have this plus t to the power 5t. And so now I want to see this. What is this? This part. Okay. So this part is okay. So between x and x to the power a, then we have a sum of AP square by P square. And I want to see, so this is going between y and from y to x. And you remember that AP depends on the absence or presence of Ziegel zeros. Okay. So let me try to bound this. This is equal to, so you remember what we are doing. We are proving Bombieri's theorem still. So this is equal to x to the power CR, okay, log x square. And then this part AP square by P. I'm interchanging AP square by P. And when does this happen? This happens when x is greater than this one, t to the power 5. So this is true if x is greater than t to the power 5. So let us assume this. Let us assume that this is true. Okay. So you remember where alpha was. Where was our alpha? Our alpha was between alpha from the first theorem was less than equal to C1 by log T. And now this is less than equal to 1 minus 1 upon C6 10 to the power 4. Yeah. For some effective constant C6. Okay. So I now take, so there I have t to the power 5, and I have from my previous blackboards, x should be, so either x here is greater than t to the power 5, and before that we had x was greater than b. So if I take the bigger of the two, that's fine. So x is greater than or equal to t to the power, the bigger of the two, so the maximum of 5 and b. Okay. So now we are going to go back to this series, and So what is it? Chi of no, it's not chi of, it's n of number of complex zeros. So alpha, t, and chi. Okay. Taken over all chi. Okay. And summed over all q. And q is what we assume is less than or equal to capital T, this T. Yeah. So put back the things that we had till now, and what do we get? So this is less than equal to, which are the x's that we get? Here. So this one is less than, so here, and we assume this is true. So now this one is less than, therefore, x. I get an x. So some c, which c am I at? I've forgotten. C6, so maybe this is C7. 1 minus alpha by log x square all right, and then the new one, this new summation, which is between x and x bar a, and it's this one, yeah, ap square by ap. So finally, what happens is we estimate this, the sum of ap square by p, x, my range of summation is from x to x bar a. What is this bounded by? This is bounded by so here this is bounded by log of x square if beta 1 does not exist, all right, and by x to x bar a, ap square by p, this is less than this we have not shown, delta 1 log x cube when if beta 1 is an exceptional zero, and chi 1, is there a chi 1 somewhere? No, there's no chi 1. So So actually, this is an exceptional character. All right. So this still remains to be shown. That's not difficult, so I won't do it. And once this is done, the proof is complete. All right. This, we could call it a different lemma. Bombieri calls this lemma C. Okay. Okay. Let me also give it a name. Show that. This, let me call it lemma 5. So lemma 5 is easy. All right. And that brings us to the end of a long proof. All right. So, and what had I told you? I had told you that I was going to show you an application of this. There's one interest that we see something non-trivial. The second interest is that we see an application. And the application, remember, was for the nice problem which everyone likes. That's the Goldbach problem. So is this okay? Have you do you want me to leave it on the board? Or you already have it? It's okay. So now our story is use of an application of the Bombieri repulsion theorem, which is stronger than the Linux or Doering. So the repulsion theory was first given by Doering and Heilbronn, and then subsequently by Linux, and this seems to be the best result known, or at least it's a very good result. I don't know if it's the best result or not. So, and use of Bombieri's repulsion theorem. So now we will announce the Goldbach conjecture. Remember this? This says that every even integer, yesterday we saw that every large even integer, integer larger than 2, okay. 2 is the sum of 2 primes. Okay. So yesterday we saw that every odd integer which is large is the sum of 3 primes. So there is no no comparable result here. We can't say that this is true for large. We can say it's true for small things because that's been verified. And small, I mean, they're small in the sense, in the sense that it's small. It's something like 4 into 10 to the power 24 or something like that, which is big for us, but it's not a big number. Yeah, 4 into 10 to the power 24. It's for the moment. It's as big as a computer can go. Yeah, the number of bits cannot exceed this for some reasons which I'm not an expert on. So up to this has been verified. The Goldbach conjecture has been verified up to where it can be verified for the moment. There are other things that are known about this is that the set on which it will fail, the Goldbach conjecture, which is called the exceptional set, and that's got nothing to do with the exceptional zero. It's just called the one where it's called exceptional because it will be where the Goldbach conjecture will be false, may be false. This is small. This can be proved, and this has been proved a long time ago. It has been proved in the 1930s, and people are getting better results on that. But of course, they haven't proved that this set is empty. Okay. So then other things happen. So one of the things that people do is they conjecture things. Yeah, this is already a conjecture. And there is a conjecture of Hardy and Littlewood. Hardy and Littlewood, they conjecture, I should introduce the notation first. Okay, so we write G of n for the Goldbach function. Yeah, so G of n notation, G for Goldbach, G of n is the number of ways of writing n as the sum of two primes. And 2 does not divide m1, m2. Okay, let's not call it G of n. I will call this little g of n. And this is, if you count this once, then the question is whether little g of n is always greater than 0. So like the previous cases, I will use P1 plus P2 here, okay, where P1 and P2 are primes, and then move from primes to von Mangold. And then capital G of n, we will write it as lambda m1, lambda m2. This is von Mangold. N is equal to m1 plus m2, not so that lambda will detect the primes and attach a log for it. But that's small. It is a small thing. In the long run, it doesn't matter. And you can get back from here to here. And you don't want 2 to divide the power. Yeah, which means that you don't want one of them to be 2. Okay, so so now Hardy Littlewood conjectured something. They said that G of n is very close to, is asymptotically n times S of n. This is the Hardy Littlewood conjecture. This was in 1912 or something like that, a long time ago. And what is S of n? And this S of n is a singular series. This is equal to, you saw the singular series yesterday, remember? You saw singular series for the ternary case also. So this is equal to 2c product of p dividing n, p greater than 2, 1 plus 1 upon p minus 2. So this one, this is a function here, this is a multiplicative function, and this c is a constant. C is a constant. It's equal to the product of p greater than 2, 1 minus 1 upon p minus 1 square. Okay? So you have a product of a constant and a multiplicative function, which makes this singular series. And yes, this just for an anecdote, this constant also appears in the twin prime problem. It's called the twin prime constant. Do you know what the twin prime problem is? Have you heard of the twin prime problem? There are infinitely many primes which differ by 2. Okay, so at the moment it is known that, I mean, this is a difficult problem, and this gap is, I think, at 356 or something like that. If you take the distance to be not 2 but larger, then then there are infinitely many primes, but we are still not at 2. So that's this constant appears there. It's sometimes called the twin prime conjecture. You might see it sometime. So okay, so this is the Hardy-Littlewood conjecture. You can state this conjecture in a weaker form. So let's call this the weak Hardy-Littlewood conjecture. I mean, a weaker form of a conjecture is of course better. So this weak Hardy-Littlewood conjecture was this was done by somebody called Phi. So weak Hardy-Littlewood conjecture this says that G of n can be between, and so no, instead of an asymptotic, it's 2 minus delta, the same S of n into n, and on the other side, this is delta S of n into n. So this is a weaker form of the Hardy-Littlewood conjecture. Okay? So it was proved recently that if this conjecture is true, if the weak Hardy-Littlewood conjecture is true, then there are no Siegel zeros. This seems somewhat intriguing, like they seem to be unrelated questions, but like they are related. Okay, so I mean, this is, so that's the weak Hardy-Littlewood. That's okay. So the theorem is, that's a recent result. So theorem, assume that the weak Hardy-Littlewood conjecture is true. Of course, if the weak Hardy-Littlewood conjecture is true, if you can prove it with the weak Hardy-Littlewood conjecture, then you can also prove it with the Hardy-Littlewood conjecture. I mean, it's better when the conjecture is weaker because you're asking for less. Then there are no zeros of any Dirichlet L functions where in sigma greater than 1 minus C log Q T plus 2. You know this one? So, which means that there is no Siegel zero. All right? So, this is a theorem of 2022. And it was proven by Goldstone. Wait, let me get the order correct because in alphabetical order. Goldstone, Ivanich, no, Friedlander first. Friedlander, F, and Surya Jaya. Okay. So there are 4 people, they proved this in 2022. So as I said that they are all living people and Surya Jaya is a young woman. Okay. She's very young and very energetic. And well, the others are old, but never mind. They are people that, I mean, they are not Riemann or anything like that. They're people like they walk around, they go to conferences, they do normal things. Yeah. So this was proved by them. And I mean, all the details of the proof are not, because it requires a lot of some preparation. I just want to tell you how they use this. Yes, you have a question? So I want to just tell you how they use Bombieri's theorem. So what they do is they go in the same way as we did for the ternary Goldbach conjecture. So they create, first of all, this function S of Q. You remember this function? We had it yesterday. So G of n, this is the G of n that counts the number of, almost counts the number of prime decompositions of n in 2 parts. I mean, the von Mangold function, it's a weighted version. So exponential minus n by n. So G of n is that G of n. Which one? It's not here. Okay, so G of n is this. Okay, the weighted Goldbach generating function. So this is the S of Q that they take, which is classical. The way is this G is for 2, but earlier the G was for 3. Okay, and then they estimate this S of Q in 2 ways. two ways. On one side, they use the known results. Yeah. So, so on one side, they have something like this. You have S of n exponential minus n by n little n congruent to 0 mod q, and n even. This one is equal to n square by phi of q 1 plus big O of q by n half. All right. So where they use the known results, the known estimates for L functions, like the sort of things you know, nothing more sophisticated than that. Okay. And then they show that S of q, this S of q, as I said, they do it in two ways, and then they bring this S of q between they assume the weak Hardy-Littlewood conjecture. Then they apply Bombieri's theorem. All right. And then they come to something, I mean, this is very sketchy, but my aim is not to give you a proof. My aim is to just tell you that such things exist. Okay. So having done this, they managed to prove that this S of q, it can be S of q. This is between 2 minus delta n square by phi q 1 plus big O of 1 by log n. And on the other hand, this is between delta n square phi of q 1 plus O 1 plus log n. So this gives then delta. So this result is possible if you assume the weak Hardy-Littlewood conjecture and apply the Bombieri's theorem. Bombieri's theorem is true. You can apply it. There's no problem in it. The question is whether we can assume the Hardy-Littlewood conjecture. That's conditional. All right. So then this happens, and this gives us a consequence that 1 plus chi minus of 1, you remember your chi, plus sub epsilon qn, which we can bound, is between 2 minus delta and delta. And this epsilon qn can be bounded by delta by 2 using Bombieri's theorem. Okay. And this therefore gives us that 1 plus psi minus 1 is equal to either 0 or 2 if delta 1, if beta 1 exists. And this is not true, okay? So this is a contradiction. Hence, beta 1 does not exist. Okay. It's to tell you that I can show you an application of this theorem in something that is non-trivial. Well, of course, it's non-trivial. I mean, usually you don't use Pombieri's theorem for proving, I don't know, for proving that there are infinitely many primes or something like that. Maybe you can, maybe there's some proof that comes from there. It's not required. Let's put it that way. So it's a use of this. I think that's about all that I wanted to tell you in this 2 weeks. I mean, and yes, so we can do in the remaining time. We can do some questions, some exercises that we had started or not started. So there was one I remember about this mu of n that caused some confusion. We could have a look at that. Did you think about it? It really requires nothing. So perhaps there was something wrong in the way we wrote it. Of course, if in such a theorem you can come to an unconditional result, then that's very nice. The reverse implication is not true. That is, if you assume that there are no Siegel zeros, this does not imply it does not imply the non-existence, it does not imply the Hardy-Littlewood conjecture. I mean, I'm saying this without knowing. I mean, I don't think it's true. Nobody has proved that it is true. It's unlikely to be true. It's not an equivalence. It's one way. Okay. There are equivalence results, but this one is not an equivalence result. It just means there are no Siegel zeros. Otherwise, absence of Siegel zeros, that I don't know what can be shown on that. Okay, so these might give you some questions that you might want to work on them. So, all right. What was our question last time? The question was, we had a question. Here, this was our question. Mu of, we had u, v of n, which were positive integers. It's an exercise. Product and u of u and v is less than equal to n. Then for little n less than or equal to capital N, mu of n is mu of b, mu of c, bc divides n, b less than equal to u, c less than equal to v, plus mu of B, mu of C, BC divides N, and the other case, B is greater than U, C is greater than V. So what happened to this? Somewhere there was some objection to what we had written, and you think this statement is wrong? A bit louder? 35. Why 35? Just like that, for fun. Okay? Okay? N equal 35, U equal, V equal to, okay? And so you want to take the, what is your little n? No, little n. Capital N is 35, right? Huh? Little n is also 35. Little n is less than equal to n, okay? So mu of 35, this is equal to 1. Why should it be 1? Huh? 35 is 5 into 7. Ah, yeah, okay. So now if I do it this way, what happens? What is mu of B? So there is no BC. Because 35 is 5 into 7. But 1 and 1, if B is equal to 1, I should correct this somehow. I've been talking for 1 week. You can talk for a while. Come. So, okay, tell me loudly so that I understand. The counting is not right. Oh. So, yeah, so shall we try to do this? We did a lot of difficult theorems. We should be able to do a simple exercise, right? So, I don't know. It seems to, I thought I had a way to do it, but like then you said that it was wrong, so then you didn't find a new way to do it. So it's, if you find a mistake, you have to correct it. So that's important. So is it true that mu of n? What am I saying? I'm saying this, that mu of n. So this is equal to mu of B, mu of C, where BC divides n. Is this correct? Yeah, I can write it like that. Then nobody can stop me from writing it like this. Which means I can write this as as mu of C and mu of B, where C divides N and B divides N by C. Huh? This is hmm? Mu of, yeah? Yeah. Mobius inversion formula. Yeah. So is that okay still? Can I still write something more or less correct? Yeah? Shall I write it? Is this okay? Okay. So what I wanted to do last time was to divide this into 4 sums. And then there was some problem. So what happened? Did you think about that? Who thought about it? No one. So last time I said I wanted to break this up into T1, T2, T3, T4 by saying that because there's an additional condition, UV is less than equal to capital N. Yeah. So this can be, so B, U and V, product of U and V is less than equal to N. So it's not the whole range. You are taking, you, one of them is less than U and the other one is less than V. Yeah. So you have N is equal, you have product of something into something is less than equal to N, but you are not running over the whole thing because U is, B is less than U and C is less than V. So something it's breaking here. Okay. So C is less than V. I think this is what has to be used to prove this. So if you write mu of N for all of the whole the whole set, then what happens? Is this all right? B is less than equal to U, C is less than equal to V, all right? Plus B is greater than U, C is less than equal to V. That's what I said last time, I think. B is less than equal to U, C is greater than V, and then the two of them are equal, are both, B is larger than U and C is larger than V. And can we find some condition in this? That was the question. And I had thought that the 2 and the 3 were equal, but somehow you didn't accept that. No, yeah, that the 2 was equal to -1. So it maybe the 2 and 3 are not equal, but hmm? Yeah, so this part in the middle should become 0. So this should be 0. Yeah? No, this should be 0, but there is a negative, all right? There is a negative here. So, yeah? I don't think that there is anything complicated in the story, except that somehow we haven't managed to do that. Okay, less than u and greater than u. And maybe we can write it like this. We can complete it in this way, I think. So mu b, mu c, bc divides n. Then suppose c is less than equal to v. Okay, this can be written as c divides n. C is less than equal to v, mu c, and then you can use, for example, the Kronecker delta, delta Cn. Okay, and this is equal to 0 if v is less than n. No, this is equal to 0. When is this equal to 0? This is equal to 0. Yeah, if c is less than n. Because if c is equal to n, then where's my capital N? Huh? Yeah, C divides capital N, and so if C is less than here, this should be N. Is that right? Okay. N, exactly. Exactly. Yeah. So that means that T1 plus T3 is going to be 0. T1 plus T3 is 0. Similarly, yeah. T1 plus T3 is 0, and T1 plus T2 is also 0. Therefore, the mu of n, yeah? My mu of n is minus T1 plus T4. So, was that what we wanted to show? Good. Okay. So it wasn't false. We did a lot of very difficult things and then we got stuck with a. Okay, so thank you all for all your patience and listening to all sorts of things. For those of you who are coming to the north, we will meet again soon. For those of you who are not coming to the north, we will meet somewhere else. Okay.